In this video tutorial, we will look at different gas laws. The gas laws we'll be looking at in this course describe the relationships between volume, temperature, and pressure. The first gas law we'll be looking at is Boyle's law. Named after Robert Boyle, it describes volume and pressure as being inversely proportionate so long as temperature remains constant. So as long as the temperature does not change, by increasing the pressure on a gas, you decrease the volume of the gas. We say this is an inverse proportionality because increasing one component decreases the other. So they have an opposite or inverse relationship. Now the reason why we use 1 over P to represent inverse proportionality is because as you increase the volume, placing this value where pressure is located in the denominator causes this value to slowly decrease, going from 1 to a half, to a third, to a quarter. So this allows you to show an inverse proportionality, whereas one variable increases, the other variable decreases. Now it's important to note that proportionate and equal are not the same thing. So V being proportionate to 1 over P is not the same as saying V is equal to 1 over P, because these numbers are not equal. I'm going to take a look at this. 1 and 1, that's equal, but 2 and 0.5, that's not equal. 3 and a third, that's not equal. So this equal sign and this proportionality sign are two different things. Although it's good to know how these variables are proportionate to each other, the equal sign is more mathematically useful to us. So in order to change the proportionality symbol into an equal sign, we graph experimental data relating volume to pressure. Now when we plot volume and pressure data, we get this little curve, which is not particularly useful for us. However, if we plot volume versus 1 over P, we found the data seems to line up in a nice straight line. Now if you recall, slope is equal to rise over run. In this case, rise is the volume and run is the inverse pressure. But when it comes to a linear line, the slope at any point on this line is always going to be identical. So the slope at point 1 is V1 over 1 over P1. And when dividing fractions, we just multiply by the reciprocal. So therefore V1 times P1 is the same as V1 divided by 1 over P1. But the same can be said at point 2. Using V2 divided by 1 over P2 gives me V2 times P2. But since this is a linear line and both slopes are identical, so slope number 1 equals slope number 2, we can now say that V1 times P1 is equal to V2 times P2 because these slopes are identical. But this relationship only works if the temperature remains constant, if the temperature does not change. The moment the temperature changes, we can no longer use this equation. And this equation is called Boyle's law. So let's try a sample question. I do recommend that you use the GRASS method, where G stands for the given, so what values are you given? R stands for required, so what are you trying to find? A is the approach, so what equation are you going to use? S stands for solve, well, solve it. And the final S is your statement. The reason why I recommend you use the GRASS method is to help you organize your information. In future questions, you'll be dealing with multiple pressures. Pressure 1, pressure 2, pressure 3, and multiple volumes and multiple temperatures. And suddenly it's very easy for you to mix up V1 with V3 or T2 with T1. And all it takes is one goof up and suddenly your question and your calculations are all over the place. So use the GRASS method, keep your information organized. Alright, so a balloon has a volume of 4.50 liters. So I write 4.50 liters is the volume. But this occurs at standard temperature pressure. Now be careful. Right now it tells you what STP is, but in future questions they may not tell you what is STP. You have to know that standard temperature is 273.15 kelvins and standard pressure is 101.3 kilopascals. But I'm going to write those values down here. It is then submerged in liquid. At this point I'm going to stop. By reading the statement, it tells me that I'm under a new situation now. So there's new conditions popping up. So now I need to add a subscript of a 1, V1, T1, P1 in order to differentiate between the first scenario, the first condition, and the second scenario, the second condition. So once submerged, the liquid also at 273.15 kelvins, so T2, 273.15 kelvins, which increases the external pressure on the balloon to 110.2 kilopascals. So the new pressure, P2, is 110.2 kilopascals. It then asks, what is the volume of the balloon now? So volume 2, what is it? Now the only equation we have so far is Boyle's law, V1 P1 is V2 P2, as long as the temperature remains constant. Looking at my givens, I see the temperature did not change, so yes, the temperature is constant. I am allowed to use this equation. Now, I like to rearrange the equation before I start plugging things in, otherwise it gets a little messy. So I want to solve for V2. I got to isolate this equation for V2. And when I do so, V2 is equal to V1P1 divided by P2. Plugging these values in, I solve the equation and get 4.14 liters as my volume number 2. Now let's see if this makes sense. I had a pressure of 101.3, and then I increased the pressure to 110.2. If we increase the pressure, because it's an inverse relationship, we should be decreasing the volume. Has my volume decreased? Absolutely. It started off with 4.50 liters, now it's at 4.14 liters. Now the second law we're going to look at is Charles's law, and it states that volume and temperature are directly proportionate as long as pressure remains the same. So if I increase the temperature of a gas, it will start to move faster and vibrate more. If it moves faster and vibrates more, it's going to collide with this container wall more often. If it collides with the container wall more often, it's going to start to push the container wall up until you've increased the volume. So increasing the temperature increases the volume. Thus, they have a direct relationship. They're directly proportionate. Increasing one increases the other. This, of course, only works, though, if the pressure remains constant. Now, once again, this proportionality symbol is not particularly useful to us in this form. We want to convert it into an equal sign. And just like before, when we plot the data points of volume versus temperature, we end up with a nice linear line. By plotting the slope, rise over run, volume over temperature, because the slope of a straight line is always going to be the same, this point over here, volume 1, temperature 1, and this slope over here, volume 2, temperature 2. These two slopes are identical. Because these two slopes are identical, V1 over T1 is equal to V2 over T2, so long as pressure remains constant. And this equation is known as Charles's law. When Lord William Kelvin looked at these volume temperature graphs, he noticed that all of them seem to extrapolate back to this point over here. So taking these straight lines and extending them back, he found that every gas, didn't matter what gas it was, they all seemed to extrapolate back to this one point, negative 273.15 degrees Celsius. So he suggested that this must be the coldest possible temperature you can reach. But how can he say that? How can he make that claim? Well, once you pass this point, what happens to your volume? It becomes a negative volume. What does a negative volume even mean? So because a gas can't have a negative volume or a zero volume, this temperature you can get. And since this is the coldest temperature you can get, he decided to start a brand new scale, named after him, of course. And he said that this is 0 kelvins. Since you can't get any colder than that, you might as well start your scale right here. So while the Celsius scale is based on water, so at 0 water freezes, at 100 water boils, the Kelvin scale starts based on the coldest possible temperature we can reach and moves on from there. This point over here is given a name. It is called absolute zero because you can't get colder than that. Furthermore, the Kelvin scale is an absolute scale, meaning that there are no negative values. Now it's interesting to note that the Kelvin scale and the Celsius scale are identical in magnitude. They just have different starting points. So if you increase by 15 degrees Celsius, you are increasing by 15 kelvins. And if you decrease by 5 Celsius, you're decreasing by 5 kelvins. So these two temperature scales are identical. They just have different starting points. To convert from Celsius to Kelvin, we add 273.15. But to convert from Kelvin to Celsius, we subtract by 273.15. So press pause and try to convert each of these temperatures to the Kelvin scale or the Celsius scale. When you're ready, press play and we'll take it up. So at 25 degrees Celsius, to convert to kelvins, we add 273.15 because the difference from here to here is 273.15. And to get from 0 degrees Celsius to 25 degrees Celsius, I have to add 25. Well, if you're adding 25 here, you're going to have to add 25 to here as well. So remember, the Celsius scale and the Kelvin scale, identical in magnitude, just different starting points. So 25 plus 273.15 gives you 298.15. Add 273.15 to these two values, and this is what you get, 248.15 and 423.15 kelvins. Obviously, going in reverse is going to be the opposite. Instead of adding, we subtract. So therefore, you get 99.85 degrees Celsius negative 175.15 degrees Celsius, and 151.85 degrees Celsius. Now it's very important, from this point on, we never use the Celsius scale in our calculations. You must always convert Celsius to kelvins. You have no choice. You must always convert to kelvins. Now why is that? Imagine, if you will, I have a block of metal, and this block of metal is negative 15 degrees Celsius. I would like you to warm up this block of metal so it's twice as hot. Well, what's the temperature now? It was negative 15 degrees Celsius. I want it to be twice as warm. Well, 2 times negative 15 equals negative 30 degrees Celsius. But that doesn't make sense. Twice as hot and yet it's colder? So dealing with negative values, especially negative temperatures, can be confusing. But that's not a problem with the Kelvin scale, because the Kelvin scale is always going to be a positive scale. All right, it's an absolute scale. It'll never go into the negatives. So that's one reason why we prefer the Kelvin scale to the Celsius scale. We don't have to worry about negatives, and we don't have to worry about the confusion involved with negatives. The second reason why we don't like the Celsius scale is because of the 0 degrees Celsius. Tell me, what happens if I divide by 0? It's undefined. The equation becomes a mess. Does that mean we're not allowed to do any chemistry when it's 0 degrees Celsius outside? Since we're never really going to deal with a 0 in a Kelvin scale, you don't have to worry about this issue. Alright, so make sure from this point on, we always convert Celsius into kelvins. Never, ever, ever do your calculations on the Celsius scale. Alright, let's try the sample question. A 14.5 centimeter cubed sample, I'm going to stop right there, because centimeter cubed is a volume. Alright, so 14.5 centimeter cubed sample of oxygen gas at 24.3 degrees Celsius. So I'm going to write down the temperature as 24.3 degrees Celsius, but I should automatically convert to kelvins, which is 297.45 kelvins, is drawn into a syringe with a maximum volume of 16 centimeter cubed. So now that I have a second volume, I'm going to set up my two conditions. Make this situation number 2 and make this situation number 1, V1 and T1. It then asks what temperature is needed to cause the plunger to pop out of the syringe, so I'm looking for T2. So I'm going to use Charles's law for this situation. V1 over T1 equals V2 over T2. Rearranging this equation, we get T2 is equal to V2 T1 divided by V1. So make sure you brush up on your basic algebra skills. If you're unable to rearrange equations like this, you need to remedy that situation immediately. But plugging our values in, punch this in the calculator, and we get 1231 kelvins, or 958 degrees Celsius. Now the question doesn't specify which units it wants for temperature, so I'd probably just leave it at 1231 kelvins. There's no need for me to convert it back to Celsius, unless that's what the question was asking for. Alright, so the only variable we have left to compare is temperature and pressure. And according to Gay-Lussac, they have a direct proportionality so long as volume remains constant. Now this law is my favorite law because it gives us refrigeration and air conditioning. Now if you ever see the phrase rigid container, that's usually a hint that we're going to be using Gay-Lussac's law, because a rigid container is one that does not change its volume. So an example would be a fire extinguisher or a spray paint can. If those containers are changing volume, that means they're exploding. But as long as it remains intact, its volume won't change, so we refer to them as rigid containers. Now with these rigid containers, they usually warn you not to expose them to heat. So don't throw a spray paint can into a fire, because as you heat it up, the gases inside start to move faster and faster, colliding with the walls more often and increasing the interior pressure. And if the pressure builds up high enough, this rigid container doesn't stay rigid for long. It explodes, sending shrapnel all over the place, creating a health hazard. So, according to Gay-Lussac, as you increase the temperature, the gas begins to increase its pressure inside as well, so long as that volume remains constant. Now, once again, it's nice to know that they are directly proportionate. Increasing one increases the other, but I prefer to have an equal sign. And once again, plotting the data, rise over run, we get a nice straight linear line. This allows us to equate the two slopes, giving us the equation P1 over T1 equals P2 over T2, so long as volume remains constant. And this is called Gay-Lussac's law. And as I mentioned earlier, Gay-Lussac's law helps us to explain how refrigerators work, or how air conditioners work. In both cases, they act as a heat pump. If you recall, the first law of thermodynamics states that you cannot create energy, you cannot destroy energy. And these refrigerating devices don't just magically make the heat disappear, they have to move the excess heat somewhere else. And that's where the second law of thermodynamics comes into play. energy always moves from high temperature to low temperature. So for instance, if I have a hot cup of coffee, energy always moves from the hot coffee to the air. You usually don't see the air heating up the cup of coffee and making it hotter. So energy always moves from high to low. Now, if you've ever seen the back of a refrigerator, you see these little grill lines. This is done in order to maximize surface area, allowing us to exchange heat over a wider surface. And inside these coils is usually a gas. And as this gas flows through the compressor, well, guess what the compressor does to the gas? It increases the pressure of the gas inside these tubes. And according to Gay-Lussac's law, temperature and pressure are directly proportionate. So if I increase the pressure, I also increase the temperature of the gas inside. And as I mentioned before, heat or energy always moves from high to low. Since these tubes now carry a hot gas, heat is released out the back of the fridge. It is quite warm back there. But eventually the gas arrives at something called an expansion device. This releases the pressure on the gas, lowering the pressure when it's inside the fridge. And according to Gay-Lussac, if pressure decreases, the temperature of the gas inside these tubes also decreases. And just like before, temperature always moves from hot to cold. Well, this burger is a lot hotter than the gas inside here, so it gives up its heat to these evaporating coils. And that is how your food stays cold. Now eventually this gas will get recycled back to the beginning, where it'll go back into the compressor and increase its pressure again. In so doing, it drops off its heat on the outside, and that is what I mean when I say that refrigerators and AC units are heat pumps. They take heat from inside, carry it over here, and pump it outside. So the heat energy doesn't just magically disappear, it has to move somewhere else. In this case, it's being pumped out of the interior into the exterior. And now you know how refrigeration works. All right, let's try this question out. A refrigerator contains a gas that exerts 110 kilopascals of pressure. So pressure equals to 110 kilopascals at a temperature of 45 degrees Celsius. So T equals 45, but I need to convert this to kelvins. So 318.15 kelvins. The gas is then allowed to expand such that the pressure decreases to 89 kilopascals. So because this is a new situation, I'm going to write P2 equals 89 kilopascals, while P1 and T1 are labeled here. Now be careful with the wording. You'll notice it says decreases to 89 kilopascals. Sometimes the question may say decreases by 89 kilopascals. And changing this small little two-letter word changes the entire question. When I say decreases to 89 kilopascals, I mean the final pressure is 89 kilopascals. But if I say decreases by 89 kilopascals, I need to subtract the original by 89 kilopascals, turning it into 21 kilopascals for P2. So please read carefully. Decreases to or decreases by has two different meanings. All right, so I need to solve for T2. We're going to use Gay-Lussac's law. P1 over T1 equals P2 over T2. Rearranging the equation, I get this. Once again, be careful with your algebra. And plugging our values in, we get 257.41 kelvins. All right, and that concludes our lesson on gas laws.